Look around you right now, not at the objects in the room, not at the walls or the ceiling, but at the space between them, at what you'd normally dismiss as nothing, because what seems to be nothing turns out to be the most consequential thing in the universe. The space you're ignoring, the invisible air between your hands, the void between the planets, the terrifying emptiness between galaxies, none of it is actually empty. And the moment you truly understand what fills it, you will never look at reality the same way again. This isn't a gentle nudge toward a new way of seeing, it is a complete demolition of the old one. What physics has uncovered over the last century is not an update to how matter works. It is a revelation about what matter actually is. And the answer is so strange, so counterintuitive, so radically different from anything our senses tell us, that even the scientists who discovered it spent decades arguing about whether to believe it. The universe is not made of particles, not at its foundation. At its deepest, truest, most irreducible level, reality is woven from something that has no edges, no surface, no single location, something that cannot be held or weighed or pointed to, something that fills every cubic centimeter of the cosmos and has done so since the first fraction of the first second after the universe began. We call them fields. And by the time this journey ends, you will understand that every electron, every atom, every molecule, every star, every thought you have ever had is nothing more than a ripple in something vast and invisible and eternal. If this kind of exploration stirs something in you, a quick like and a subscription would mean a great deal to us. It helps us keep making content like this. Before we arrive at the quantum revolution, before we reach the mind-bending territory of fields that flicker and particles that wink in and out of existence, we need to start somewhere older, somewhere that feels more comfortable. Because the story of how physicists came to understand quantum fields is not a story that begins in a laboratory. It begins with a question that haunted natural philosophers for thousands of years, a question so deceptively simple that it's easy to overlook just how deeply strange it truly is. How does one thing affect another thing it has never touched? Think about gravity. Right now, as you sit or stand or lie reading these words, the Earth is pulling you toward its center. You feel it. It is the most constant, most intimate force you have ever experienced. But here is the question that Isaac Newton, for all his towering genius, could never satisfactorily answer. How does the Earth do that? Your feet may be touching the ground, but what about the moon, which hangs 250,000 miles overhead? What about Mars? What about the distant stars, whose light takes years to reach us, and whose gravitational influence nevertheless ripples outward in every direction? Newton's law of gravitation, published in 1687, was a triumph of mathematics. It could predict the arc of cannonballs. It could calculate the orbits of planets with breathtaking accuracy. It told you exactly how strong the gravitational force between two masses would be if you knew their sizes and the distance between them. What it could not tell you, what Newton himself admitted with visible discomfort in his private correspondence, was the mechanism. How does Earth reach across the void and grab the moon? There is no rope between them, no physical medium connecting one to the other, nothing, as far as anyone could see, crossing the gap. Newton called this action at a distance. He knew the mathematics worked. He knew the predictions were correct. But he also knew that action at a distance was philosophically monstrous. The idea that an object could exert force on another object across a perfect vacuum with no physical connection of any kind struck him as borderline occult. He spent the rest of his life unable to explain it, and for nearly 2 centuries after him, no one else could either. The person who first began to crack that mystery was not a university professor. He was not the product of aristocratic education or elite scientific circles. He was a bookbinder's apprentice from South London named Michael Faraday, who had almost no formal schooling and taught himself science by reading the books he was paid to bind. By any standard measure, Faraday should never have become one of the most important scientists in history, but he possessed something rarer than a university degree. He had the ability to see, not just to observe data or collect measurements, but to see into the invisible structure of nature and to describe what he found there in terms that went beyond mathematical abstraction. When Faraday scattered iron filings around a magnet and watched the tiny metal slivers arrange themselves into curving arcs that fanned outward from pole to pole, he did not see a pretty demonstration effect. He saw a physical reality that everyone else had been refusing to take seriously. The space around the magnet was not empty. It was structured. It had shape. It was doing something. Faraday called what he saw lines of force, and in his notebooks and lectures over the following decades, he proposed something that the respectable scientific establishment largely dismissed as the romanticism of an untrained mind. He proposed that the force between two magnets did not leap across empty space at all. Instead, each magnet created a real physical entity in the surrounding space, an entity that extended outward in all directions, threading through the air and the walls and the vacuum, filling the region around the magnet with something that had properties and structure. When a second magnet was brought into that region, it did not interact with the first magnet across the intervening distance. It interacted with the entity that the first magnet had created in the space immediately around it. The interaction was always local, always immediate. The thing that bridged the distance was real and present and physical, even if no one could see it or touch it directly. This was the concept of the field, born in the imagination of a man with no mathematics but extraordinary vision, and it would change everything. The mathematician who gave Faraday's vision its full power was James Clerk Maxwell, a Scottish physicist whose name belongs alongside Newton and Einstein in any honest account of scientific greatness. Maxwell took Faraday's intuitive pictures of invisible lines threading through space and translated them into a set of equations, compact, precise, almost elegant in their economy. Between 1861 and 1865, Maxwell published what are now called Maxwell's equations, and they described something that Faraday had suspected but never been able to prove. Electric fields and magnetic fields were not separate phenomena. They were two aspects of a single unified thing, the electromagnetic field. And the electromagnetic field was not merely a mathematical convenience or a visualization tool. It was a physical entity in its own right. It existed in space. It stored energy. It could carry forces across the universe. It was real. But then Maxwell's equations produced a result that even he found astonishing. They predicted that under certain conditions, the electric and magnetic components of the electromagnetic field could sustain each other in a self-reinforcing oscillation. A changing electric field would generate a magnetic field. That magnetic field, as it changed, would regenerate the electric field. And this loop, this dance of two fields feeding each other, could propagate through empty space entirely on its own, needing no medium, no material carrier, nothing but the field itself. Maxwell calculated the speed at which this propagating disturbance would travel. When he worked through the mathematics, the number that emerged was approximately 186,000 miles per second. He recognized it immediately. It was the speed of light. In that moment, an entire ancient mystery dissolved. Light, which humans had been wondering about since the first philosophers asked why the sky was bright, turned out to be a wave in the electromagnetic field, not a wave in any material substance. Not a vibration of air or water or any other medium. A wave in a field that permeated all of space, and not just visible light. Radio waves, invisible to human eyes, were electromagnetic waves of lower frequency. Infrared radiation, ultraviolet light, X-rays, gamma rays, all electromagnetic waves, all ripples in the same field, differing only in how rapidly they oscillated. The electromagnetic field connected everything. It was everywhere, and its waves were the most familiar thing in human experience. This discovery forced a revolution in how physicists thought about space itself. Before Maxwell, empty space was conceived as a passive backdrop, a container in which matter existed, and through which forces mysteriously acted. After Maxwell, space was anything but empty. Space was filled with the electromagnetic field. At every point in the universe, at every moment in time, the electromagnetic field had a value. Even in the most remote and desolate regions between galaxies, where no atom had ever drifted, the electromagnetic field was present. It was a fixture of reality as basic as space and time themselves. The field was not in space. In a deep sense, the field was part of what space was. And this was only one field. Gravity would eventually demand its own field-based description, one that came from Einstein's general theory of relativity in 1915, and which recast gravitational force not as an invisible reach across a void, but as the curvature of space-time itself. The mass of the sun does not pull on the Earth through empty space. It warps the geometry of space-time around it, and the Earth, following the straightest possible path through that warped geometry, traces the arc we call its orbit. The gravitational field is the curvature of space-time. It is present everywhere. It carries energy. It propagates changes at the speed of light. When two impossibly massive black holes spiraled into each other, 1.5 billion light-years from Earth, in an event that released more energy in a fraction of a second than all the stars in the observable universe radiate. In that same time, the gravitational field shuddered. Ripples in space-time itself spread outward in all directions. And in September of 2015, those ripples reached Earth. They compressed and stretched space by less than 1,000th of the diameter of a single proton, and a pair of instruments called LIGO detected them. The gravitational field, the curvature of space-time, had carried news of that ancient cataclysm across the universe and delivered it to human detectors. The field is real. It was never a metaphor. So by the early 20th century, the conceptual framework was in place. Space was not empty. It was filled with fields. Fields carried energy and transmitted forces. They connected distant objects not through mysterious action at a distance, but through the physical properties of a medium that permeated all of space. But this classical field picture, for all its elegance, was about to encounter something it could not survive. It was about to meet the quantum, and when the two collided, what emerged was something that neither camp had seen coming. Something stranger than classical fields. Something stranger even than quantum mechanics. Something that would ultimately reveal not just how matter behaves, but what matter fundamentally is. The collision began, as so many revolutions do, not with a grand experiment, but with a nagging irritation, a problem that should have been simple but refused to behave. Physicists in the late 19th century were trying to understand how a heated object radiates light. When you heat a poker in a fire, it begins to glow, first dull red, then brighter orange, then yellow-white as the temperature climbs. The exact distribution of radiation across frequencies, how much red, how much orange, how much ultraviolet and beyond, followed a pattern that experimenters could measure with great precision. What they could not do was explain that pattern using the tools of classical physics. The mathematics of Maxwell's electromagnetic theory, applied to the problem of a heated object, produced a catastrophic prediction. It said the object should radiate infinite energy at high frequencies. Not a lot of energy, not more than expected. Infinite energy. The calculation simply ran away to infinity and refused to stop. This failure, which physicists called the ultraviolet catastrophe, was not a minor embarrassment. It was a sign that something was fundamentally wrong with the classical picture of fields and radiation. Into this crisis walked Max Planck, a German physicist known for his caution and his conservatism. A man who preferred to build carefully on established foundations rather than to tear them down. Planck did not want to overthrow classical physics. He was trying to save it, but the only way he could reproduce the experimentally measured curve of radiation was to introduce an assumption so radical that he himself initially refused to take it literally. He proposed that electromagnetic energy was not emitted and absorbed continuously in any quantity, the way water can be poured in any amount. Instead, energy came in discrete packages, minimum units below which you could not subdivide. He called them quanta, from the Latin word for amount. Each quantum of electromagnetic energy at a given frequency carried an energy equal to a specific constant, now called Planck's constant, multiplied by the frequency. This meant that at high frequencies, each quantum carried so much energy that the heated object couldn't easily produce them. The radiation fell off at high frequencies, just as experiments showed it did. The catastrophe was averted, but at what cost? Classical field theory said energy was continuous. Planck was saying it was granular. The apparent smoothness of light was an illusion produced by the enormous number of quanta involved. At the fundamental level, light came in chunks. 5 years later, Albert Einstein pushed this further than Planck had dared. Einstein proposed that light didn't merely come in chunks when it was emitted or absorbed. Light was always chunked. The electromagnetic field itself was quantized. Its energy existed in discrete, indivisible packets. Now, Einstein called them light quanta. We now call them photons. With this idea, Einstein explained a phenomenon called the photoelectric effect, which had been baffling experimenters for years. When light shines on a metal surface, It can knock electrons loose. The strange thing was that the energy of the ejected electrons didn't depend on how intense the light was. It depended on the color of the light, on its frequency. Dim blue light could eject electrons with more energy than blazing red light, no matter how bright the red light became. Classical field theory had no explanation for this, but if light came in discrete packets whose energy depended on frequency, it made perfect sense. Each photon carried a specific energy determined by its color. When a photon hit an electron in the metal, it either had enough energy to kick the electron free or it didn't. Intensity just determined how many photons arrived per second. It didn't change what each individual photon could do. The photoelectric effect confirmed Einstein's picture. Light was quantized. The electromagnetic field came in chunks. And this discovery, rather than relativity, is the work for which Einstein would eventually receive the Nobel Prize. But here is where the story takes the turn that nobody anticipated. Because if the electromagnetic field was quantized, if its energy came in discrete packets that behaved like particles when they interacted with matter, then what exactly was the relationship between the field and the particle? Was the photon a particle that happened to be associated with an electromagnetic wave? Was it a wave that happened to behave like a particle in certain circumstances? Was it both? Was it neither? The question was not philosophical. It had razor-sharp experimental edges. When physicists directed a beam of light through two narrow slits, the light produced an interference pattern on a screen behind, a pattern of alternating bright and dark bands that could only be explained if light was a wave. Two waves emerging from two slits overlapped and combined, reinforcing each other in some places and canceling each other out in others. Only waves could do that. Particles traveling in straight lines would just make two bright patches behind the two openings. But when the light intensity was turned down so low that only one photon passed through the apparatus at a time, something impossible appeared. Each individual photon still, over time, contributed to the same interference pattern. A single photon was somehow interfering with itself. It was going through both slits at once. It was, in some sense, everywhere the wave was, and also nowhere until it hit the screen and left a single, localized mark. The photon was behaving like a wave when no one was watching, and like a particle when someone was. This was not a paradox that could be resolved by being cleverer or by designing a better experiment. It was a fundamental feature of nature, and understanding it required a completely new mathematical framework. That framework, developed in a frenzy of genius between 1925 and 1928, was quantum mechanics. Quantum mechanics described particles not by definite positions and velocities, but by wave functions, mathematical objects that spread out through space and encoded probabilities. You couldn't say where a particle was before you measured it. You could only say how probable it was to find it in each possible location when you did. The particle existed in a superposition of all possible states simultaneously, and the act of measurement forced it into one definite state with a probability determined by the wave function. This was not an admission of ignorance, not a statement that the particle was somewhere specific and we just didn't know where. It was a statement about the nature of reality itself. Before measurement, the definite properties simply did not exist. They were created by the act of observation. This was the world at its smallest scales, irreducibly probabilistic, irreducibly strange. But quantum mechanics in its original form carried a fatal limitation that became clear the moment you tried to combine it with Einstein's special theory of relativity. The quantum mechanics of the 1920s described a fixed number of particles. You wrote a wave function for one electron, or two electrons, or 50. But however many you started with, you kept. The mathematics had no mechanism for creating new particles or destroying existing ones. And special relativity, through the most famous equation in science, said something quite different. E equals mc squared. Energy and mass are equivalent, interchangeable. Given enough energy concentrated in a small enough region, matter can be created from pure energy. Given matter and its mirror image antimatter in close proximity, both can be annihilated into pure energy. Particles were not permanent, they were transient, and any theory of nature that claimed to be fundamental would need to accommodate their creation and annihilation without flinching. This was the problem that a new generation of physicists had to solve, and the solution they found, quantum field theory, was not merely a technical patch, it was a complete reconceptualization of what particles were. The key move was to take the concept of the field, which classical physics had established as the primary physical entity in the universe, and apply the full formalism of quantum mechanics to it. Not to quantize a particle moving through a field, but to quantize the field itself, to allow the field to have quantum states, to fluctuate, to exist in superpositions. And when physicists made that move, something extraordinary happened. Particles did not have to be put into the theory. They fell out of it naturally. They were inevitable consequences of quantizing a field. Here is what that means. Imagine the electromagnetic field, which you can think of as an entity that has a value at every point in space. In classical physics, this field can oscillate with any amplitude, any frequency, any energy. The oscillation can be as gentle or as violent as you like. There is no minimum energy, no smallest wave. But when you apply quantum mechanics to the field, you discover that the field cannot oscillate with just any energy. Just as the electron in an atom can only occupy certain discrete energy levels, the electromagnetic field can only vibrate in discrete energy steps. The field can have no quanta of excitation, or 1 quantum, or 2 quanta, or a trillion, but not 1.5. The energy of the field comes in indivisible minimum units, and each one of those minimum units of excitation is what we call a photon. The photon is not a particle that exists inside the electromagnetic field the way a marble might sit inside a jar. The photon is the electromagnetic field vibrating with a single quantum of energy at a given frequency. The field is the thing. The photon is what the field does when it carries its minimum possible energy. Remove all the photons from a region of space and the electromagnetic field is still there. It has not disappeared. It has merely returned to its lowest energy state. The substrate remains, the excitations are gone, and now comes the part that rewrites everything. Because the electromagnetic field is not the only quantum field in the universe, it is one of many. For every type of particle we have ever detected, there is a corresponding quantum field that pervades all of space. There is an electron field, and every electron that has ever existed is a single quantum of excitation of that field. There is an up quark field, and every up quark and every proton in every atom of every star is an excitation of that field. There is a down quark field, a muon field, a tau field, 3 distinct neutrino fields. There are fields for the particles that carry the strong nuclear force, the gluon fields. Fields for the particles that carry the weak nuclear force, the W and Z boson fields. Each one fills all of space. Each one is always present. Each one is invisible, intangible, and absolutely real. The space around you right now is not filled with one field. It is saturated with dozens of them, all overlapping, all coexisting, all vibrating at their quantum ground states, unless something disturbs them and kicks them into excitation. Every particle you have ever seen, every atom, every molecule, every stone, every raindrop, every human body, every galaxy, is nothing more than a collection of localized excitations distributed across these fields. The fields came first. The particles are what happens when the fields are disturbed. This shift from particle to field as the primary entity is not a subtle technical refinement. It is a revolution in ontology, a complete restructuring of what we mean when we say something exists. Consider what it means for a particle to be an excitation of a field rather than an independent object. In the old picture, an electron was a thing. It had a location. It had a mass. It had an electric charge. It existed in its own right, independently of anything else. You could, in principle, pick it up and move it, and it would remain itself wherever you took it. It was a noun. In the field picture, an electron is more like a verb. It is something the electron field does. It is an event in the field, a concentrated region of activity, a localized disturbance that propagates through the field according to quantum mechanical rules, and that can be created or destroyed depending on whether the field gains or loses a quantum of excitation. It is not a thing that has properties. It is a process that manifests properties. The difference is not semantic. It has consequences that reach into every corner of physics. One of the most immediate and dramatic consequences is that creation and annihilation become completely natural. In the particle picture, the creation of a new particle from nothing is deeply mysterious. Where did it come from? Particles do not simply appear. But in the field picture, what we call particle creation is merely an increase in the excitation level of a quantum field. The field was always there. It was in its ground state, unexcited. When sufficient energy arrives, the field responds by producing a quantum. A particle appears not from nothing, but from the energy that disturbed a field that was already present. Particle annihilation is the reverse. A particle and its antiparticle, which is an excitation of the same field with opposite quantum numbers, can combine in such a way that the excitations cancel. The field drops from a two-quantum state back toward its ground state. The energy that was stored in those excitations does not disappear. Energy is always conserved. It flows into neighboring fields, creating new excitations, new particles of different types. The electron and positron that annihilate each other deposit their combined energy into the electromagnetic field, producing photons. One field loses quanta, another gains them. The total energy is preserved, no creation from nothing, no destruction to nothing, just the perpetual rearrangement of excitation across a web of interconnected fields. At particle accelerators like the Large Hadron Collider at CERN, this process plays out on a breathtaking scale. Two protons, each one a tight cluster of quark and gluon field excitations, are accelerated to within a tiny fraction of a percent of the speed of light and then directed into each other. The collision concentrates an enormous amount of energy in a region smaller than a proton itself. In that tiny, blazing, momentary furnace, the quantum fields go wild. The electron field, which everywhere in the universe is in its ground state waiting quietly, gets kicked into excitation. An electron and a positron appear where none existed a moment before. The muon field produces a muon and an anti-muon. Fields associated with particles too heavy to be created in any natural environment on Earth are excited for the first time in the laboratory, producing particles that live for tiny fractions of a second before cascading back down into lighter excitations. The detectors surrounding the collision point record the tracks and energies of hundreds of particles per collision event. And physicists read those records like seismologists read the traces left by an earthquake, reconstructing from the aftermath what fields were briefly excited, what quantum states flared into existence and then decayed, what the underlying field structure of reality is doing at its most extreme. Every particle that appears in those detectors is not a constituent of the proton that was hiding inside it. The proton didn't contain electrons waiting to pop out. The electrons were created in the collision, created from the energy that excited a field that had been present all along, filling every corner of the LHC, filling every corner of the universe, simply waiting for enough energy to arrive and disturb it. Now, we need to pause and confront something even stranger than the existence of quantum fields, something that sits at the center of quantum field theory, and that most popular explanations either rush past or avoid entirely. What happens when a quantum field is as undisturbed as it can possibly be? What is the state of a quantum field when no particles are present, when there are no excitations, when you have removed every particle from a region of space as completely as you possibly can? The answer is that the field is not quiet, it is not still, it is not at rest. Quantum mechanics forbids it. This is because of the uncertainty principle, one of the deepest and most uncompromising truths about the universe. The uncertainty principle, discovered by Werner Heisenberg in 1927, says that certain pairs of physical properties cannot both be precisely determined at the same time. The more precisely you know one property, the less precisely you can know the other. Position and momentum are the classic example. The more exactly you pin down where a particle is, the less you can know about how fast it's moving. But the uncertainty principle applies to fields as well. It says that you cannot simultaneously know both the exact value of a field at a point in space and the exact rate at which that value is changing. If the field were perfectly still, you would know both. The value would be zero, and the rate of change would also be zero, both simultaneously and exactly known. The uncertainty principle forbids this. It is not that we lack the instruments to measure both. It is that no such state of affairs can exist in nature. Nature itself prohibits it. The consequence is that quantum fields in their ground state, their lowest possible energy configuration, are never still. They fluctuate. Constantly, everywhere, even in a region of space that has been emptied of every particle, even in the most perfect vacuum that physics can describe, the quantum fields are seething with activity. Their values jitter up and down in tiny random fluctuations that cannot be suppressed because they are required by the fundamental nature of quantum reality. These fluctuations are called vacuum fluctuations, and they are not a theoretical convenience or a mathematical artifact. They are physically real, and they have consequences that have been measured in the laboratory with extraordinary precision. The most celebrated demonstration of vacuum fluctuations is an effect predicted in 1948 by the Dutch physicist Hendrik Casimir. Casimir showed mathematically that if you place two flat, uncharged metal plates very close together in a vacuum, they would experience a force pushing them toward each other. Not because of electric charge, not because of any ordinary force, but because the vacuum fluctuations of the electromagnetic field between the plates are constrained in ways that the fluctuations outside the plates are not. The plates act like walls that restrict which fluctuation modes are allowed in the gap between them. Outside the plates, all modes are free. Inside, only certain modes fit. The result is a difference in the vacuum pressure on the two sides of each plate, and that difference produces a net force pushing the plates together. This force, the Casimir force, was confirmed experimentally in 1997. Two metal plates in empty space, with nothing between them but the quantum vacuum, attracting each other because of the activity of a field in its supposedly lowest energy state. The vacuum is not nothing. It is the ground state of quantum fields. And the ground state of quantum fields is rich with physical consequences. Perhaps more remarkable is what vacuum fluctuations do to particles that exist within them. An electron, which we might naively imagine as a clean, isolated point of charge moving through empty space, is in reality immersed in a constantly fluctuating sea of vacuum activity. The electromagnetic field around the electron, even in empty space, is never perfectly still. It fluctuates. And those fluctuations interact with the electron, affecting its energy levels and its electromagnetic properties. The most dramatic evidence for this comes from a measurement made in 1947 by the American physicist Willis Lamb. Using techniques that had been developed during wartime radar research, Lamb measured the energy levels of the hydrogen atom with unprecedented precision. He found that two energy levels that quantum theory predicted should be exactly identical were in fact slightly different. The difference was tiny enough to have escaped detection with any earlier instrument, but it was unmistakably real, and it could be explained only by the interaction of the electron with the vacuum fluctuations of the electromagnetic field. The constantly flickering quantum vacuum was shifting the electron's energy by a measurable amount. The theoretical calculation using the full machinery of quantum field theory agreed with Lamb's measurement to better than 6 significant figures. That agreement was one of the early triumphs of quantum electrodynamics, the quantum field theory of electromagnetism, and it confirmed beyond any reasonable doubt that the quantum vacuum was physically real and physically active. The empty space through which the electron moved was not empty at all. It was alive with fluctuations that permanently shaped the electron's properties. Quantum field theory has since been tested to levels of precision that beggar description. The magnetic moment of the electron, a quantity that measures how the electron responds to a magnetic field, has been calculated from the full theory of quantum electrodynamics to an accuracy of about 1 part in 10 billion. The corresponding experimental measurement, done with equipment so sensitive it can detect differences equivalent to measuring the distance from New York to Los Angeles to within the width of a human hair, agrees with the theoretical prediction to the same extraordinary level. No other prediction in the history of science, in any field, across any discipline, has been confirmed to this degree of precision. Whatever quantum field theory is, it is capturing something about the nature of reality that is deeply, profoundly correct. Let us now look at the full landscape of quantum fields that modern physics has identified, because the picture in its completeness is one of the most striking achievements of human thought. The standard model of particle physics, which describes 3 of the 4 known forces in all known matter, is at its heart a theory of fields. 17 distinct quantum fields have been identified, each one filling all of space, each one always present. 6 of them are the quark fields: the up quark field, the down quark field, the charm quark field, the strange quark field, the top quark field, and the bottom quark field. These fields and their excitations are the constituents of protons and neutrons, which are in turn the building blocks of atomic nuclei. 6 more are the lepton fields: the electron field, the muon field, the tau field, and 1 neutrino field for each of the 3 charged leptons. Leptons are the particles that do not feel the strong nuclear force. Electrons, the particles that orbit atomic nuclei and that drive all of chemistry, are excitations of the electron field. The electromagnetic field is one of the remaining fields, its excitations being the photons that carry light and all electromagnetic radiation. 3 more fields carry the weak nuclear force, the force responsible for radioactive decay and certain nuclear transformations, their excitations being the W and Z bosons. The gluon fields, 8 of them, carry the strong nuclear force, the force that binds quarks together inside protons and neutrons, and that holds atomic nuclei together against the electromagnetic repulsion of their constituent protons. And finally, there is 1 more field, the one that was the last to be confirmed experimentally, discovered at CERN in 2012 after decades of searching. This field, unlike every other one we have discussed, has a non-zero value everywhere in the universe, even in the absence of any excitation. While the electromagnetic field has a value of 0 in a perfect vacuum, this field does not. It is switched on everywhere, always, filling every point in the cosmos with a constant background value. And the consequence of this non-zero background is that particles which interact with this field acquire mass. The more strongly a particle interacts with it, the more massive it becomes. Particles like photons, which do not interact with it at all, remain massless and consequently travel at the speed of light. The particles that do interact with it are slowed, in a sense, by the interaction, dragging through the field background the way a swimmer drags through water. This is the origin of mass, not an intrinsic property of particles, not a fixed quantity stamped onto them at creation, but the result of an interaction with a field that permeates all of space. The excitation of this mass-giving field is a particle called the Higgs boson. Its detection at the LHC in 2012, after a 40-year search involving thousands of physicists and the most complex scientific instruments ever constructed, was one of the great culminating moments in the history of science. Not because the particle itself was particularly dramatic. It decays in less than a millionth of a billionth of a billionth of a second, but because its existence confirmed the field. And the field was the prize. Now let us talk about something that sounds like science fiction, but is, in fact, established physics. Something that reveals just how strange and how rich the quantum vacuum really is: virtual particles. In quantum field theory, the vacuum fluctuations we have been discussing can, under certain conditions, briefly produce what look like real particles. But they vanish before they can be detected directly, before they can be observed in any permanent way. They are called virtual particles. The uncertainty principle, again, provides the mechanism. The same principle that says you cannot simultaneously know a field's value and its rate of change also says something about energy and time. A quantum system can temporarily borrow energy from the vacuum as long as it pays it back before a time determined by how much it borrowed. The larger the borrowed energy, the shorter the time before it must be returned. So, the quantum vacuum is constantly producing and absorbing these transient excitations, particles that flicker into existence for immeasurably brief moments and then vanish. They cannot be caught directly. No detector is fast enough to record them, but their effects on real particles are measurable, and they have been measured. The Lamb shift that we discussed earlier is one result of virtual particles. The anomalous magnetic moment of the electron is another. These effects can be calculated by summing over all the virtual particle states that can transiently appear in the vacuum, a calculation that requires the full mathematical apparatus of quantum field theory, and that results in predictions that agree with experiment to extraordinary precision. Virtual particles are not real in the sense that they can never be directly observed, but their effects on the universe are completely real. They are part of what the quantum vacuum does. Forces themselves in quantum field theory are transmitted by virtual particles. This is one of the most beautiful and profound results of the entire theoretical framework. In the old classical picture, forces acted through fields, and the fields were continuous. In the quantum picture, the fields are quantized, and the force between two particles is carried by the exchange of virtual quanta of the relevant field. When two electrons repel each other, the repulsion is mediated by virtual photons being exchanged between them. One electron disturbs the electromagnetic field, producing a virtual photon that travels to the other electron and kicks it. The kick is the force. The virtual photon is the carrier. In diagrams that Richard Feynman invented to represent these calculations, the exchange process is depicted as two electron lines meeting through an intermediate wavy line representing the photon. These Feynman diagrams are not just convenient pictures, they correspond precisely to terms in a mathematical calculation of the interaction probability. And when you add up all the possible diagrams, all the ways the virtual photons can be exchanged, including the diagrams where a virtual photon briefly turns into a virtual electron-positron pair and then recombines, you get the extraordinarily precise predictions that quantum electrodynamics is famous for. Every force you have ever experienced, the electric force that holds atoms together, the magnetic force of a compass needle, the strong force that keeps atomic nuclei intact, the weak force that powers certain types of nuclear decay, all of them are, at their quantum foundation, the exchange of virtual field quanta. Forces are conversations between fields, conducted in the language of virtual particles. There is a consequence of the field picture that has implications not just at the atomic scale, but at the scale of the entire cosmos, because the vacuum fluctuations of the quantum fields contribute energy to the vacuum itself. Empty space is not energetically inert. Every quantum field, in its ground state, carries a zero-point energy, the minimum energy that the field must have because of the uncertainty principle's prohibition on perfect stillness. Summing up the contributions from all the quantum fields gives a total vacuum energy. And this vacuum energy has a physical consequence. Einstein's general theory of relativity says that energy gravitates. All forms of energy, including the energy of the quantum vacuum, curve space-time and affect the expansion of the universe. When physicists first calculated the total vacuum energy expected from quantum field theory and compared it with what cosmological observations implied it could be, they found a discrepancy, a staggering discrepancy. The theoretical prediction and the observational limit differed by roughly 120 orders of magnitude, one followed by 120 zeros. This is the largest numerical disagreement between theory and observation in the history of physics. It is called the cosmological constant problem, and it remains one of the deepest unsolved mysteries in all of science. Something must be canceling the enormous vacuum energy predicted by quantum field theory down to the much smaller but non-zero value that observations indicate. What that cancellation mechanism is, no one knows. But the vacuum energy, whatever its precise value, is real. It drives the accelerating expansion of the universe. The universe is not only expanding, it is expanding faster and faster, pushed apart by the energy of the quantum vacuum, by the zero-point fluctuations of the fields that fill all of space. The quantum vacuum, the fizzing ground state of reality, is the engine of cosmic acceleration. The smallest scale and the largest scale are connected through the fields. Now consider what the field picture reveals about identity. About the stunning fact, confirmed by every experiment ever performed, that all electrons are absolutely identical to one another. Not similar, not nearly identical, identical to as many decimal places as any measurement has ever achieved. The same mass, the same charge, the same magnetic moment, the same spin. Every electron in every atom, in every molecule, in every living cell, in every star, in every galaxy across the observable universe is the same as every other electron, without a single detectable exception. In a world where particles were independent objects, this would be an almost miraculous coincidence. Objects made by any manufacturing process, natural or artificial, always have small variations. Snowflakes, crystals, atoms assembled from quarks by the strong force, all of them carry tiny individual differences. Why would electrons be different? Why would they be manufactured to such perfect uniformity? The field picture answers this question cleanly and elegantly. All electrons are identical because all electrons are excitations of the same field. There is one electron field. It fills the entire universe. When it is excited by one quantum of energy at one location, the result is an electron. When it is excited at another location, the result is another electron. But both excitations are of the same field. Both are governed by exactly the same underlying physics. Both carry exactly the same properties because those properties are not the properties of independent objects, but the properties of the field itself expressed in its minimal excitation. The electron in the hydrogen atom in a distant galaxy and the electron in the hydrogen atom in a water molecule in your blood are the same type of thing, not because of some mysterious universal manufacturing standard, but because they are both expressions of a single universal field. The field is one. Its excitations inherit its singularity. This is not a mathematical abstraction. It is a physical reality with experimental consequences. Quantum statistics, the rules governing how collections of identical particles behave, have been tested exhaustively. The Pauli exclusion principle, which says that no two electrons can occupy the same quantum state, is a direct consequence of the quantum field nature of electrons and is confirmed by the existence of every atom more complex than hydrogen. Without it, all electrons in every atom would collapse to the lowest available energy state. All chemistry would be impossible, and complex molecules, including the molecules of life, could never form. The identity of electrons is not incidental. It is what makes the world possible. The question of what particles are doing between measurements when you are not looking at them is one of the oldest puzzles in quantum mechanics, and the field picture offers a perspective on it that is both more precise and more unsettling than the usual account. When we say that an electron is an excitation of the electron field, we are saying something about the field's global state, not just about a localized bump in it. A real excitation of a quantum field is described by a wave function that, in principle, extends across all of space. The electron is not somewhere with a question mark attached. The electron's wave function is genuinely spread out, and the probability of detecting the electron at any given location is determined by the amplitude of the wave function at that location. The excitation propagates through the field according to the Schrödinger equation, or, in the relativistic version, the Dirac equation. When you measure the electron's position, the wave function collapses, and the excitation is found to be localized at a specific point. But before the measurement, the excitation was delocalized. It was everywhere its wave function had support. The electron in this picture is not a small thing moving through a field. It is the field in an excited state, and that excited state has a probability amplitude at every point in space. This picture makes the double-slit experiment, that old quantum paradox, much cleaner. The photon going through two slits is not a particle that somehow manages to go through both. It is an excitation of the electromagnetic field, and that excitation propagates through the entire apparatus as a wave, consistent with the wave nature of the field. The photon's wave function goes through both slits. When it arrives at the detection screen, the wave function gives a probability distribution that reflects the interference of the two pathways. When the photon is detected, the field excitation is absorbed, and a definite localized event occurs. The wave function collapses. The photon is found at a specific point. But the distribution of many such events, built up over time, follows the wave function's interference pattern. The particle behavior and the wave behavior are not contradictory. They are different aspects of the same field excitation, seen in different experimental contexts. There is a deeper reason why fields must be more fundamental than particles, one that goes beyond the convenient explanation of why electrons are identical, or why particles can be created and destroyed. It has to do with the most basic requirement we would ask of any fundamental description of reality, that it be the same for all observers, that it not depend on who is doing the observing, or how fast they are moving, or where in the universe they happen to be. Relativity has taught us that many apparently objective quantities, the length of a rod, the rate at which a clock ticks, the simultaneity of two events, turn out to be observer-dependent. They depend on the relative motion between the observer and the system being observed. This is not a failure of measurement. It is a feature of reality. But we would hope that the truly fundamental entities, the bedrock substances from which reality is made, would be independent of the observer's state of motion. Fields satisfy this criterion. The quantum state of a field, the full mathematical description of what the field is doing at every point in space and time, is the same for all observers. They may describe it differently, using different coordinate systems, but the physical content is the same. Particles do not satisfy this criterion. The number of particles present in a given region of space is not observer-independent. This is not a paradox or an edge case. It has been worked out rigorously and has a name: the Unruh effect. The Unruh effect, predicted theoretically by William Unruh in 1976, says the following: an observer at rest in empty space, in a region containing no particles, will measure precisely what you would expect: no particles. But an observer who is uniformly accelerating through that same region of empty space will measure something different. They will detect a warm bath of particles surrounding them. Not the same region of space, but different description. The accelerating observer experiences the vacuum as filled with thermal radiation, particles with a temperature proportional to the acceleration. The two observers agree about the state of the quantum field. The field is in its vacuum state. They disagree about whether particles are present, because the concept of a particle is not absolute. It depends on how you divide the field's quantum states into what counts as a particle and what counts as the vacuum, and that division depends on the observer's state of motion. This is one of the clearest demonstrations in all of physics that particles are derived, observer-dependent entities, while fields are the objective underlying reality. A similar phenomenon occurs near black holes. Hawking radiation, first predicted by Stephen Hawking in 1974, describes a situation where the intense curvature of space-time near a black hole's event horizon causes the quantum fields to produce particles in a way that a distant observer can detect. An observer falling freely through the event horizon detects nothing unusual. The quantum fields in their vicinity appear to be in their normal vacuum state. But the distant observer, for whom the event horizon represents an absolute boundary, sees the black hole emitting a faint glow of thermal radiation. Again, two observers disagree about the particle content of the fields. The fields are the common ground. The particles are the interpretation, and the interpretation depends on context. If you want a description of reality that is the same for all observers, you must work with fields. The particle description is a useful approximation, enormously convenient and practically indispensable for most purposes, but fundamentally secondary. A reading of the field that depends on who is doing the reading. The quantum fields that fill the universe are not passive. They interact with each other. This is where forces come from, in the deepest sense. When physicists say that two electrons repel each other, what they mean in the language of quantum field theory is that the electron field couples to the electromagnetic field, and that this coupling causes the excitations of the two fields to influence each other. The electron field, when excited, disturbs the electromagnetic field around it. The electromagnetic field disturbance propagates. When it reaches another region where the electron field is excited, the disturbance affects that excitation. The coupling between fields is what we experience as force. The mathematical rules governing how fields couple to one another, rules encoded in the equations of the Standard Model with extraordinary precision, determine every interaction that every particle has ever had or will ever have. Chemistry is the electromagnetic field coupling between electron fields in different atoms. Nuclear binding is the strong force fields coupling between the quark fields inside protons and neutrons. Radioactive decay is the weak force fields coupling between quark fields and lepton fields, and mediating the transformation of one type of excitation into another. Everything that ever happens in the material universe is a coupling between quantum fields, a conversation between invisible entities that fill all of space and that we have only recently, in the last century of human history, begun to hear. Let us dwell for a moment on what the strong nuclear force tells us about quantum fields, because it illustrates the field picture with unusual vividness and reveals a feature that has no analog in classical field theory. The strong force which binds quarks together to form protons and neutrons and binds protons and neutrons together within atomic nuclei is described by a theory called quantum chromodynamics, QCD. The fields that carry the strong force are the gluon fields, and unlike the electromagnetic field, they interact with each other. The photon, the excitation of the electromagnetic field, has no electric charge. It does not feel the electromagnetic force. It carries the force without being subject to it. Gluons, the excitations of the gluon fields, carry something analogous to charge, called color charge, and they interact with other gluons. They feel the force they carry. This self-interaction gives the strong force a peculiar character. Whereas the electromagnetic force between two charges weakens as the distance between them increases following an inverse square law, the strong force between two quarks does not weaken with distance. Pull two quarks apart, and the gluon fields between them behave like a rubber band, maintaining a roughly constant tension regardless of how far apart the quarks are pulled. The result is confinement. You can never isolate a single quark. If you try to pull one quark away from its partners, you must supply increasing energy to maintain the separation. Eventually, you supply so much energy that it is sufficient to excite the quark fields and create a new quark-antiquark pair. The original quark remains bound to its new partner. You cannot isolate it. Every quark that has ever been created in the lab has instantly combined with other quarks or antiquarks into composite particles. No free quark has ever been detected. This is not because quarks are firmly stuck together with some mechanical glue. It is because the gluon fields, the quantum fields that carry the strong force, have a structure that makes it energetically impossible to separate the excitations of the quark fields that they bind together. The field dynamics make isolation impossible. The field is the confinement mechanism. There is a mystery inside this story that physicists have not yet fully solved. Why do the quantum fields that we have discovered have the properties they do? Why are there 6 quarks and 6 leptons? Why are there 3 generations of matter, each a heavier copy of the first? Why do the coupling constants, the numbers that describe how strongly each field couples to the others, have the specific values they do? The Standard Model accommodates these values. It measures them, encodes them, and uses them to make predictions. But it does not explain them. It does not tell us why the electron has the mass it does and not some other mass. It does not explain why there are exactly 3 generations. It does not reveal why the coupling strengths are what they are. The Standard Model is extraordinarily successful, but it is in this sense incomplete. It is a description of the fields we have found, without being an explanation of why those fields, why those values. The quest for that deeper explanation is the frontier of theoretical physics. String theory, loop quantum gravity, theories of grand unification, all of them are attempts to find a framework from which the Standard Model emerges as a consequence rather than as a given. The fields we know may themselves be excitations of something deeper, something we do not yet have the mathematical tools to fully describe. Every revolution in physics has replaced what seemed fundamental with something more fundamental beneath it. The quantum fields of the Standard Model may be the penultimate layer, not the last. Gravity stands apart from this story, and its separateness is one of the central mysteries of modern physics. The other 3 forces are described by quantum field theories that are consistent with special relativity, and that have been tested to extraordinary precision. Gravity resists this treatment. Einstein's general theory of relativity, the best theory of gravity we have, describes the gravitational field not as a field living in space-time, but as the geometry of space-time itself. The gravitational field is not in space. It is the structure of space. And quantizing the structure of space-time turns out to be enormously more difficult than quantizing fields that live within it. When physicists try to construct a quantum field theory of gravity, the calculations produce infinities that cannot be controlled by the standard mathematical techniques used to handle infinities in other quantum field theories. This does not mean that quantum gravity is impossible. It means that the framework of quantum field theory, as we currently understand it, is not powerful enough to handle it. Something new is needed. String theory proposes that the fundamental entities are not zero-dimensional point particles, and not even the fields associated with point particles, but one-dimensional vibrating strings. Different vibrational modes of these strings correspond to different particles. In this picture, quantum fields emerge as an approximation that becomes accurate when strings are too small to be resolved. The graviton, the hypothetical particle that carries gravity, emerges in string theory as one of the vibrational modes of the fundamental string. Loop quantum gravity takes a different approach, attempting to quantize the geometry of spacetime directly by treating space itself as discrete at the smallest scales. In loop quantum gravity, there is a minimum length, the Planck length, roughly 10 to the power of minus 35 meters, below which the concept of distance loses meaning. Space is not a smooth, continuous fabric. but a network of discrete quantum states. Both approaches are incomplete. Neither has yet made a prediction confirmed by experiment. The problem of quantum gravity remains open. The deepest structure of reality, the place where quantum mechanics and general relativity must somehow be reconciled, is still dark to us. And yet, for all that remains unknown, what we do know is extraordinary. We know that the universe is filled with quantum fields. We know that every particle is an excitation of one of those fields. We know that the forces between particles are the exchange of virtual quanta of the fields that couple them. We know that the vacuum is not empty, but is the seething ground state of those fields, alive with fluctuations that have real, measurable consequences. We know that the identity of all particles of the same type is not a coincidence, but a consequence of their all being excitations of the same field. We know that the number of particles in a given region of space is not an objective, observer-independent quantity, while the state of the quantum fields is. We know all of this to a level of experimental precision that no other scientific framework in history has approached. The picture that emerges is one of extraordinary coherence and depth. The universe at its foundation is not a collection of things. It is a collection of processes, of fields, vibrating and coupling and exchanging excitations across the whole of space-time, from the first instant of the Big Bang to whatever future the cosmos holds. And it is worth sitting with what this means, not just for physics, but for how we understand ourselves and our place in what exists. You are made of atoms. Your atoms are made of protons, neutrons, and electrons. Your protons and neutrons are made of quarks bound by gluons. Your electrons are excitations of the electron field. Your quarks are excitations of the quark fields, the electromagnetic interactions that hold your atoms together, that power the chemistry of your cells, that let neurons fire and muscles contract and eyes see. All of those are the electromagnetic field at work, virtual photons being exchanged between charged excitations of the matter fields. The light that enters your eyes and lets you see the world is the electromagnetic field vibrating. The warmth you feel from the sun is energy carried by that same field across 93 million miles of space. Every sensation you have ever had, every perception, every thought and memory and emotion, all of it arises from the activity of quantum fields. You are not separate from those fields. You are not an observer watching them from outside. You are made of them. You are a particular arrangement of excitations in the electron field and the quark fields and the fields that carry the forces between them, organized into atoms, organized into molecules, organized into cells, organized into the incomprehensible complexity that is a living, thinking human being. The boundary between you and the world is not where it appears to be. The fields that constitute your body are the same fields that fill the space around you. The electron field in your hand is continuous with the electron field in the air between your fingers and in the stars overhead, and in the most distant galaxies at the edge of the observable universe. It is one field. There is no edge to it. There is no gap in it. It is everywhere and always. When the atoms that were once inside a star explode in a supernova and scatter across the galaxy, the excitations of the quantum fields that compose those atoms are destroyed, and new excitations are created. But the fields themselves are not destroyed. They cannot be. They are the fabric. The excitations come and go, created and annihilated in the endless churning of the cosmic fields. The fields remain. When those scattered atoms, those new excitations of ancient fields, eventually find their way into clouds of gas and dust and collapse under gravity into a new star with new planets, and on one of those planets, chemistry produces self-replicating molecules, and those molecules evolve over billions of years into organisms capable of asking questions about the nature of reality. Those organisms are made of the same fields that were present in the original star. The fields are older than any particle. They are older than any atom. They have been present since the universe was hot and dense enough that no composite particle could exist, since the fields themselves were in a different phase, since the symmetries of the standard model were unbroken, and the universe was a state no human mind can quite visualize. The fields have been here through everything. The particles are their transient expressions, the moments when the fields condense into forms that bump into each other and scatter and bind and create the intricate structures we call matter. The fields are the continuity. The particles are the events. Think about what it means to hold something in your hand. A coin, say. The coin feels solid. It has weight and heft and sharp edges. It does not feel like a pattern of vibrations in invisible fields, but that is what it is. The copper or nickel that makes up the coin is a lattice of atoms, each one a cluster of quark field excitations bound by gluon field excitations forming a nucleus, surrounded by electron field excitations held in shells by the electromagnetic field. The solidity you feel is not the hardness of tiny balls touching each other. It is the Pauli exclusion principle preventing the electron field excitations in the coin from occupying the same quantum states as the electron field excitations in your hand. Two regions of excited electron field resist being in the same location, not because of any mechanical obstruction, but because of the fundamental quantum statistics of fermionic fields. The sensation of solidity, one of the most basic things you have ever felt, is the quantum field principle preventing field excitations from sharing states. The weight you feel is the gravitational field, the curvature of space-time caused by the Earth's mass, pulling the coin's field excitations toward the center of the planet. The coin's shiny surface is the electromagnetic field of the metal's free electrons responding to incoming photons and reflecting them at angles that produce the gleam. Every single property the coin has, every single sensation it produces, is a manifestation of quantum fields in their various modes of activity. The same is true of everything. Everything. The sound of rain is a pressure wave in the air, which is a field excitation density wave in the electron and quark fields of nitrogen and oxygen molecules, propagating through the medium of collisions between those excitations governed by the electromagnetic field. The color of a flower is the electromagnetic field of certain molecules absorbing photons at specific frequencies corresponding to specific quantum transitions in the electron field, excitations of those molecules, while reflecting photons at other frequencies. Those reflected photons then exciting the electron field excitations in the rhodopsin molecules of your retina. The warmth of a fire is the transfer of energy from the high-energy excitations in the burning material's quantum fields to the lower-energy excitations in your skin's quantum fields, through the electromagnetic field radiation we call infrared light. The beat of your heart is an electrochemical signal propagating along the muscle cells of your cardiac tissue. Driven by ion channels and cell membranes, those channels regulated by conformational changes in protein molecules. Those conformational changes governed by the electromagnetic interactions between atoms, every atom an excitation of quantum fields. Your thoughts, the experience of reading these words and understanding them, or struggling to understand them, or feeling curious or skeptical or amazed, that experience arises in the electrochemical activity of 100 billion neurons, each neuron made of atoms, each atom made of field excitations, the whole incomprehensible apparatus of consciousness emerging from the quantum fields, doing what quantum fields do in the particular arrangement that is your brain. You are not a stranger in this universe. You are not a visitor passing through it. You are assembled from the same raw material that makes stars and galaxies and the void between them. The same electron field that buzzes in your neurons also stretches across the cosmos. The same quark fields that constitute your atoms also build the cores of neutron stars, where densities and pressures that would vaporize any ordinary matter compress those fields into states we can barely calculate. The universe did not make you from something other than itself. It made you from itself, from the fields that are itself. When physicists aim enormous particle accelerators at each other, and smash excitations of quantum fields together with energies equivalent to temperatures 1 trillion times hotter than the center of the sun, they are not doing something alien to nature. They are doing what the early universe did. In the first fractions of a second after the Big Bang, all the fields were in states of extraordinary excitation. Energies so high that quarks could not bind into protons and neutrons. The quark fields and the gluon fields churned in a plasma of free excitations. A quark-gluon plasma that lasted until the universe cooled enough for confinement to take hold and bind the quarks into the composite particles that eventually became the atoms that became the stars. We recreate those conditions briefly and locally in our accelerators. We peer into the hot quantum field plasma of the early universe and measure its properties. We test whether the standard model's description of the fields and their couplings holds at energies we have never before accessed. And again, it holds. The theory that describes the quantum fields at energies achievable in the laboratory turns out to describe them also at energies a trillion times higher, in conditions that last for nanoseconds inside a detector chamber. The fields are robust. Their mathematical description is a deep truth, not a convenient approximation. There remains, of course, the question of what is beyond. What lies at energies and scales beyond those the LHC can reach. Whether the Standard Model's 17 fields are truly fundamental, or whether they are themselves excitations of something deeper. Whether string theory, or something we have not yet imagined, will reveal a layer of reality below quantum fields, the way quantum fields revealed a layer below particles. The history of physics is the history of discovering that what seemed fundamental was not the final answer. Atoms turned out to be made of electrons and nuclei. Nuclei turned out to be made of protons and neutrons. Protons and neutrons turned out to be made of quarks. Quarks and electrons turned out to be excitations of quantum fields. What are quantum fields excitations of? We do not know. Perhaps strings. Perhaps something else entirely. Perhaps the question is malformed, and quantum fields are genuinely foundational in a way that the objects of earlier physics were not. We do not yet have the experimental access or the mathematical tools to know. What we do know is that the answer, when it comes, will be stranger and deeper and more beautiful than anything we have imagined. Every revolution in the history of physics has exceeded the imagination of the physicists who preceded it. Newton could not have imagined Maxwell's equations. Maxwell could not have imagined quantum mechanics. The founders of quantum mechanics could not fully imagine quantum field theory. Whoever discovers what lies beyond quantum field theory will reveal a reality that we, right now, cannot quite picture. But here, at this level of understanding, what we can say is this. The world is not made of things. Not at bottom. Not at the level where you can no longer go deeper with the tools we currently have. At the deepest level we have reached, the world is made of processes, of vibrations in invisible, space-filling, time-spanning quantum fields that have been present since the universe began and that will persist as long as the universe persists. The particles that physics is famous for, the electrons and quarks and photons and neutrinos and bosons, all of them are manifestations of those fields. Brief, localized, quantized disturbances in entities that have no boundaries and no preferred location and no center. The fields are everywhere. The particles are the moments when the fields are somewhere in particular. Every atom you have ever seen or touched or breathed or been made of is a set of those moments. A constellation of disturbances and fields that span the cosmos. You yourself are a set of those moments. Extraordinarily complex, dynamically maintained, richly interconnected with the environment through the same fields that compose both you and it. You are not a collection of things moving through space. You are a pattern of events and fields that do not distinguish between you and the space around you. The distinction between self and world, so vivid and so certain in experience, so useful for navigating life, dissolves at the level of quantum fields. There is one electron field. It does not stop at your skin. There is one electromagnetic field. It carries your body's electromagnetic signals and also the sunlight that warmed the food that powered the cells that built your brain. There are the quark fields, the same quark fields everywhere. The fields make no distinction. The pattern you call yourself is real. The boundaries the pattern draws are real in the sense that matters for living. But they are not real at the level of the fields themselves. Before we arrive at that final reckoning, let us spend a moment with what may be the most quietly stunning implication of the quantum field picture. The idea that the observer and the observed are not cleanly separable in the way classical physics assumed. In classical physics, there was the world, and there was the scientist measuring it, and the two were distinct. The scientist did not affect the world by watching it. The measurement was a passive reading of something that existed independently and objectively. Quantum mechanics shattered this assumption at the level of individual particles. The act of measurement affects the system being measured. The wave function collapses. The electron, which had no definite position before the measurement, now has one because of the measurement. But quantum field theory adds another layer to this story. Because the fields are everywhere, because the vacuum fluctuates everywhere, Because even the most isolated electron is constantly interacting with the virtual excitations of the surrounding vacuum fields, there is no such thing as a truly isolated quantum system. Every excitation in every quantum field is coupled, however weakly, to every other field. The electron couples to the electromagnetic field, the quarks couple to the gluon fields, the neutrinos couple to the weak force fields. And the vacuum of all those fields is constantly fluctuating, constantly brushing against every excitation that exists. The universe is not a collection of independent things that occasionally interact. It is a web of fields in which excitations are perpetually entangled with their surroundings. The separation between systems that quantum mechanics speaks of is an idealization, a useful and enormously productive idealization, but an idealization nonetheless. In reality, nothing is fully separate. Everything is coupled to the fields and through the fields to everything else. This coupling across fields has a name when it becomes strong enough to create permanent correlations between distant parts of a system: quantum entanglement. Entanglement is one of the most discussed and most misunderstood phenomena in all of quantum physics. When two particles interact and then separate, they can remain entangled. The quantum states of the two particles are correlated in a way that has no classical analog. Measuring the state of one particle instantaneously determines what you will find if you measure the other, regardless of the distance between them. Einstein famously found this deeply troubling, calling it spooky action at a distance, and spending years arguing that quantum mechanics must be incomplete, that there must be hidden variables, some underlying classical reality, that explain these correlations without invoking genuine non-locality. In 1964, the physicist John Bell devised a mathematical test that could determine, experimentally, whether the correlations predicted by quantum mechanics could be explained by any local hidden variable theory. The tests were conducted most definitively by Alain Aspect and colleagues in the 1980s and repeated with ever greater rigor in the decades since. The verdict was unambiguous. Quantum mechanics is correct. The correlations are real. Hidden variable theories of the local kind that Einstein envisaged cannot explain them. Reality at the quantum level is non-local in a deep and unavoidable sense. Entangled particles, separated by any distance, are parts of a single quantum system described by a single wave function. Measuring one affects the description of the other, instantly, regardless of the distance. Nothing travels between them faster than light. No signal, no energy, no information. But the correlations are there, woven into the quantum state of the system from the moment the particles interacted. In the field picture, entanglement is not mysterious. When two excitations of a quantum field interact, the field develops correlations across the region that both excitations have traversed. The field state is a global object. The two excitations are not independent things that happen to share information. They are parts of a single field state that has a definite quantum character across its whole extent. Entanglement is the quantum field's way of being more than the sum of its excitations. The field is a unity. Its excitations, when they interact, partake of that unity. They become, in the language of quantum mechanics, entangled subsystems of a field state that cannot be factored into independent pieces. The non-locality of entanglement is the non-locality of the field itself, expressed in the correlations between its excitations. Entanglement does more than challenge our classical intuitions. It has become the basis of an entirely new kind of technology. Quantum computing harnesses superposition and entanglement to perform certain calculations exponentially faster than any classical computer. Quantum cryptography uses the principles of quantum measurement to create communication channels that cannot be eavesdropped without detection. Quantum sensing uses the extraordinary sensitivity of quantum systems to measure gravitational fields, magnetic fields, and time with precisions that classical instruments cannot match. The quantum fields that underpin reality are not just an abstract philosophical framework. They are an engineering resource. The same quantum properties that make fields so strange, superposition, entanglement, the probabilistic nature of measurement, are being harnessed to build technologies that classical physics could never contemplate. We are not merely observers of the quantum field universe. We are beginning, tentatively and partially, to manipulate it. Consider also what quantum field theory tells us about time itself. In classical physics, time was a stage, a backdrop against which events unfolded. In special relativity, time became dynamic, stretching and compressing depending on relative motion. In general relativity, time became part of the fabric of space-time, curved by mass and energy. In quantum mechanics, time played yet another role, the parameter along which quantum states evolved. But quantum field theory introduces a further wrinkle. Because fields can fluctuate even in their ground states, and because those fluctuations can involve the creation and annihilation of virtual particle-antiparticle pairs, the quantum vacuum has a kind of temporal richness that the classical vacuum never had. Virtual particles appear and disappear. They exist for durations determined by the energy-time uncertainty relation. At very high energies, virtual pairs can appear and vanish in fantastically brief intervals. At lower energies, they last longer. The vacuum is not a static backdrop. It is a dynamic, fluctuating entity that has its own temporal activity. And this activity, as we have seen, has real consequences for the particles that exist within the vacuum. The electron is not a clean, isolated object moving through a neutral backdrop. It is an excitation of the electron field moving through a vacuum that is constantly producing and absorbing virtual photons, virtual electron-positron pairs, virtual muon pairs, and more. These interactions shift the electron's effective mass, modify its charge distribution, alter its magnetic moment. The electron that we measure is not the bare electron of the theory. It is the bare electron dressed in a cloud of virtual excitations that perpetually surround it. The measured properties of the electron are the properties of this dressed electron, the bare excitation plus all of the vacuum interactions that inevitably attend it. This process of dressing a particle in virtual excitations, called renormalization, was one of the most controversial and eventually most celebrated developments in 20th century physics. It required physicists to be very careful about what they meant by the mass and charge of a particle. The bare mass and the bare charge are theoretical constructs. The measured mass and measured charge include the effects of all virtual interactions. Renormalization is the mathematical procedure by which the relationship between the two is made precise. It troubled some physicists deeply, including Richard Feynman himself, who helped develop it while simultaneously finding it philosophically unsatisfying. But it works. The renormalized predictions agree with experiment. The electron's properties, calculated including all virtual interactions to many orders of perturbation theory, match what is measured. The vacuum dressing of the electron is real. It has to be included to get the right answer. There is something profound in this picture. The properties we call the fundamental properties of matter, the mass of an electron, its electric charge, its magnetic moment, are not simple inherent characteristics of a localized particle. They are the result of the particle's perpetual interaction with the quantum vacuum that surrounds it. Strip away the vacuum, imagine the bare electron with no virtual cloud, and you would have an object with different properties. But you can never strip away the vacuum. The vacuum is always there. The virtual interactions are always occurring. The dressed electron is the only electron that can exist in a universe with quantum fields. The fundamental properties of matter are shaped by the field structure of the universe. Change the vacuum, change the fields, and you would change the properties of the particles. This is not a theoretical possibility. It happened in the early universe. In the first moments after the Big Bang, the fields were in different phases. The field responsible for particle masses had not yet acquired its non-zero background value. In that earlier phase, the particles were massless. They moved at the speed of light. The universe was a plasma of massless excitations interacting with frantic intensity. As the universe cooled and expanded, the fields underwent phase transitions, analogous to the phase transition that water undergoes when it freezes from a disordered liquid to a crystalline solid. The mass-giving field settled into its non-zero background state, and the particles that couple to it acquired mass. The universe we inhabit, with its massive electrons and massive quarks and protons and neutrons and atoms, is the universe that emerged from that phase transition. In a very real sense, the mass of everything in the universe is a consequence of a cosmic phase transition that occurred when the universe was less than a picosecond old. The properties of matter are not eternal and unchanging. They are the properties that the quantum field settled into as the universe cooled. They are a frozen relic of the hot quantum field plasma of the early cosmos. And what of the future? The quantum fields that fill the universe now are in a particular configuration, a particular vacuum state. But there is a possibility, taken seriously by some physicists, that this vacuum state is not the lowest possible energy state of the fields, that there might be a lower energy state, the true vacuum, into which the current vacuum could in principle tunnel. If that happened, a bubble of true vacuum could nucleate somewhere in the universe, a bubble in which the quantum fields had different values and therefore in which the laws of physics, the masses of particles, and the strengths of forces were different. That bubble would expand at the speed of light. Inside it, the physics would be different from the physics outside it. The atoms that exist in our current vacuum might not be stable in the true vacuum. The molecules that make up life might not be able to form. We would never see it coming. No signal could precede the bubble wall, which travels at the speed of light. This scenario, sometimes called vacuum decay, is not considered likely in the immediate future, and may not be possible at all if our vacuum is genuinely the lowest energy state. But its existence as a theoretical possibility tells us something important. The universe is not a fixed stage with fixed laws. It is a dynamic field configuration that happens, for now, to be in a particular state. The laws of physics as we experience them are contingent on that state. The fields are the deepest thing, and the laws are what the fields do in the state they are in. Alter the state, and you alter the laws. All of which brings us back to where this journey began, to the question of what fills the apparently empty space around you. The answer that physics has given us over the last century, through the accumulated labor of thousands of experimenters and theorists working across 2 world wars and a Cold War, and an era of extraordinary technological development, is as strange and as beautiful as any answer science has ever produced. The space around you is not empty. It is full. It is saturated with quantum fields, all of them always present, all of them vibrating at their ground states, flickering with virtual excitations, shaped by the curved geometry of space-time, ready to be disturbed into producing the particles and forces that drive every process in the physical world. The fields are the medium in which every physical event occurs. They are the substance from which every physical object is made. They are the carrier of every force, the repository of the vacuum energy that drives the expansion of the universe, the source of every particle that has ever existed or ever will. They have been here since the beginning. They will be here until, if it ever comes, the end. They are the universe's most permanent possessions, the thing it cannot be without. This is not mysticism. It is physics. The most precisely confirmed, most experimentally tested, most mathematically rigorous physics humans have ever done. The quantum fields are real. Their excitations are real. The vacuum fluctuations are real. The interactions are real. The particles are real as any excitation of any field can be. And all of it, every real thing in the universe, is the fields. Invisible, everywhere, eternal. The fabric of what exists, the substance from which the cosmos makes everything it makes, including the beings who discovered it and who now, after a century of experiment and mathematics and insight, can begin to see it for what it is. The universe looked at itself through the eyes of creatures made of its own fields, and it discovered that it was not the solid, particle-filled, thing-dense place it appeared to be. It was a vast, shimmering, interconnected web of quantum fields, alive with fluctuations, rich with excitations, generating the whole astonishing complexity of the world from the restless activity of entities that cannot be seen or touched or held, but that are more real than anything we have ever called real. That is the universe. That is what it is made of. And that, in the deepest sense any science has yet reached, is what you are made of too. And now, you know. The journey from Newton's troubled question about how forces cross empty space, through Faraday's lines of force, through Maxwell's equations, through Planck's quanta and Einstein's photons, through the quantum mechanics of the 1920s and the quantum field theories that followed, has led here. To the recognition that the universe is not a collection of objects, but a manifold of fields, that every particle is a field's way of carrying energy in its minimum unit, that the vacuum is never silent, that forces are conversations between fields conducted through virtual exchanges, that the identical properties of all particles of the same type follow inevitably from their all being excitations of the same field, that the observer dependence of particle counts, so beautifully illustrated by the Unruh effect, proves that fields are the objective reality and particles the dependent interpretation, that the Casimir force, the Lamb shift, the anomalous magnetic moment of the electron, the Higgs boson, all confirm in precise quantitative detail that the quantum field picture is not philosophy, but fact, measured to a part in 10 billion, confirmed by the most demanding experimental tests that human ingenuity has devised. You live inside a field. You are made of fields. The question that haunted Newton, the mystery of how forces reach across empty space, is resolved, and the resolution is that space was never empty. It was always full of fields, full of the invisible, quantized, fluctuating substance that makes everything that is. Look around you one more time, at the space between things, at the apparent nothing, and see it for what it is, the ground state of a quantum field universe, humming just below the threshold of perception, the deepest layer of the real.